Okay, so today's lecture is going to be covering the remainder of the concept of magnetism. We're going to start by discussing Earth's magnetic field. So Earth functions like a huge magnet, although it's not like a magnet you would hold in your hand that is a solid piece of metal. The magnetic field generated by Earth is actually caused by the motion of molten particles. So moving charges does produce electricity. Moving magnetism produces electricity. Moving electricity creates magnetism. So they're two sides of the same coin, essentially. Um, the well, obviously, we cannot go to the core, so we can't actually look at this. We can only look at evidence to support what a magnetic field is caused by. So that is the best of what we know, is that we have these currents that kind of swirl around, and that motion of charges creates the magnetic field. This is also, there's contributions, the Coriolis effect, the same way that clouds move around Earth's atmosphere due to the rotation of Earth. Those molten pathways or flows are also affected. This image here shows the rotation of Earth and then the magnetic field of Earth, and they're not aligned. We're going to talk about that more a little bit lower, but that's just to get us started. The magnetic poles are not directly at the geographic poles, and we'll talk about that in a moment here. So magnetic domains in a solid are clusters of aligned magnetic atoms. So you have a little section of atoms here that all have the same magnetic direction. And when you put them collectively together in an image like this, they're actually canceling each other out. So when you have something that's strongly magnetized, all these little domains are lined up the same direction. Now, this is not what is happening in the Earth's core, because mainly the Earth's core is molten. And so you do not have these locked, fixed, magnetized regions. So what causes magnetism in a solid is not the same as the way the Earth's core functions as a magnet, because it is molten and moving around. And we are talking here about stationary atoms and domains. So question 2, we don't know where the Earth's magnetic field comes from. We don't really know. I mean, we have speculation, we have educated guesses, we have scientific evidence, but we don't know. Its magnetic field is similar to that of a bar magnet, but it's not a magnetized chunk of iron like a magnet is. Why can't the magnetic field be explained using the concept of magnetic domains? So I just talked about that. So if you missed it, rewind and watch again. All right, this is really cool. So we think of something like the polarity of Earth, like magnetism, to be really constant and staying the same. But we have evidence on the Earth's crust, or in particularly under the ocean, that shows that the polarity of the pole of Earth actually flips every 300,000 to a million years or so. It reverses, and south becomes north and north becomes south. We don't completely understand how this happens or how quickly it happens. It is speculated that we are leading into another reversal soon. But remember, on a geological timescale, soon can be hundreds of thousands of years. So soon doesn't mean this year or even your lifetime. This is how it works. Okay, so you have a mid-ocean ridge. Okay, so essentially you have a place where the two pieces of the Earth's crust are separating. Okay, so they're separating like this. And as they separate, magma comes up through the crack and flows onto the surface of under the bottom surface of the ocean and hardens into rock. And in all of that rock are pieces of iron and ferromagnetic materials. And while they're still molten, while they're still liquid, they're going to align themselves with the magnetic field of Earth, because they're being pulled by the magnetic field of Earth. And so when they harden, then they're locked into that position and they can no longer just flip. And so what we find, if we look at the ocean's crust, there's alternating north, south, north, south, north, south as you go away from the mid-Atlantic ridge. And it is equal on either side of the ridge as well. So you have like north, north, south, south, north, north, like that. Each side is equal. Here's another image of that. This is a little bit better in terms of showing the matching. This first image shows the forming of this red strip. All right, so the Mid-Atlantic Ridge is pulling apart. The two parts of the crust are separating. And so that's where the magma is coming up and filling and hardening into rock. So this is showing normal magnetic polarity, and this is showing reverse. This is like an older deposit. Then it spreads, and this shows that it flipped, the two gray sections, and then the dark red, it flipped back. And then those separate, and then you got another reversal, and then you've got the current strip of magma being laid on the ocean floor. Now, saying normal just means that it's the same way it is right now. Normal is normal. Whenever it's the other way, that's normal, right? But for our current polarity, that's what normal is referring to. So the same polarity as we currently have. Now, of course, it's not abnormal when it's the other way. It's just natural laws. The magnetism is flipping back and forth. And it just so happens that right now, while we're measuring it and calling things normal, it's going the way it is. The Earth's magnetic field is not stable. Give some evidence of that. So right here, this is our evidence that the magnetic field is not stable. It flip-flops back and forth every so many 300, 100,000 years to a million years. All right, next topic is the concept of the magnetic pole and the geographic pole and how those are not aligned. Now, depending on what you read, you may see something like this image here. This image shows the geographic North Pole, so that's the North Pole in North America, and the magnetic North Pole. And so they're showing that the magnetic North Pole is near the geographic North Pole. This is a bit of a misconception, and it's an oversimplification, and when you actually start to break it down, it does not make any sense. So many of you are familiar with what a compass is. A compass is a little device that always points to the north to help you navigate where you are and where you're going. Now, the compass the little red arrow on a compass will point to the geographic North Pole, generally speaking, okay? And so we call the north end of a magnet the north-seeking end. So the compass, the red tip of the compass, is north-seeking, meaning it's attracted to the North Pole. Now, if you were to use a compass and a magnet, you would find that the magnet actually attracts to the South Pole of the magnet. What this actually means is that the Earth's magnetic field is actually south up, north down, meaning that if you had a compass seeks the North Pole, but it's attracted to the opposite end of a magnet. So a compass will attract towards the south magnetic pole, which is at the north geographic pole. All right. So it's actually backwards. And images like this are confusing because it shows it as magnetic north, which isn't really accurate. Magnetic north, sure, but it's the south magnetic pole. Really confusing, and the terminology is very similar. But basically, if we were to hang magnets from the classroom ceiling, which I do every year except for this year, unfortunately, all of the north ends of our magnets would actually point towards the North Pole. And the problem is that we know that opposites attract. So the north end of a magnet should be pointed to the south end of another magnet, not towards the north end. That doesn't make sense. So this picture where it shows that the north end is up at the top would not be correct, because a north end of a magnet would not attract to the north end of another magnet. It would attract to the south end. So this is actually more accurate, because if we were to hang magnets from our ceiling, the north ends would all face north, which would mean that the south magnetic pole is actually at the north geographic pole. So that's a little bit confusing, but basically it's just simply a it's kind of a misidentification of terminology. When they first started naming magnets, north seeking, and then what does that actually mean? What does attract? What does repel? And so it led to this kind of like confusion as to what that actually. All right, so we have our axis of rotation, but then we have our magnetic pole. Now notice that they don't land at the exact same spot. And that is a little bit of an issue for when you're trying to use a compass, because a compass is going to point towards the magnetic pole, not the rotational axis. So it's not going to point to the actual geographic North Pole, but all of our maps are set up to the North Pole. So how do you actually work around that? And we're going to get to that in just a moment. Here's another image of what I was talking about above. It kind of includes both of these two images. We have our geographic North and South Pole, okay? And then they call this the magnetic North Pole, just meaning that it's the place where the magnetism is centralized in the northern hemisphere, I guess you could say. And then the magnetic South Pole is where the magnetism is centered or rotates about in the southern hemisphere. So it's not actually the south what is it called up here? The south magnetic pole. It's just the magnetic South Pole, which it sounds almost exactly the same. But notice that the orientation of the magnet in the center of Earth here is south up, because a north seeking the North Pole is actually going to be attracted to the south end of a magnet, which is why it's orientated this way. So I know that's super confusing, but essentially it was a mistake in the term when they named everything, because North Pole, north seeking, not initially realizing that the Earth is functioning as a magnet itself, and the fact that it attracts means it is actually the opposite, not the same pole. And so now we're left with this like confusion. And actually the notation for North and South changed in the 50s, I want to say, the 40s or the 50s. They started reversing the way they talk about it. So it's not even consistent within the last 100 years. So that's super confusing too. All right. Does the North Pole of a magnet point to the North magnetic pole of Earth? Explain. So you can kind of go about that two ways. Either you can talk about how the North magnetic pole is actually located in the southern hemisphere, so the north end of magnet would actually point to the south magnetic pole. However, if we're talking about the magnetic North Pole, meaning like the pole that is in the north, not necessarily the north side of the magnet, then that's why you can actually answer that either way. But just as long as you explain that opposites attract, and that a north pole of a magnet should attract to the south pole of another magnet, and therefore that's what the Earth would do as well. So try to put into words what I just talked about North Pole, South Pole, and the orientation. But remember that this labeling of magnetic North Pole is more referring to the fact that it's in the northern hemisphere, not that it's the north end of the magnet. The Earth's magnetic field is actually north down, south up, and that's why a north end of a north pole of a magnet attracts to the north part of Earth, because that is where the south magnetic pole is. Yeah, so do your best to explain that when it's a little tricky. All right, the universe is shooting charged particles called cosmic rays. They are hazardous. The Earth's magnetic field actually traps them and keeps them from hitting Earth. Additionally, the sun hurls charged particles out of great fountains. It looks like geysers coming up off the sun's surface, and they hurl charged particles at the Earth. And if we did not have the atmosphere, if we did not have the magnetic field around Earth, then those things would hit Earth. They would destroy our atmosphere and everything living on the planet. So the fact that the Earth has a magnetic core actually allows for life to exist on Earth. And there's some postulating that Mars used to have a magnetic core, and for some reason it stopped, And that led to the destruction of everything on the surface of Mars. And it no longer was a planet capable of sustaining life of any kind or keeping water or atmosphere. So that's an interesting idea. So number 5, how does the Earth's magnetic field protect us from the sun? That is listed, I just talked about that just a second ago. Describe the phenomenon known as aurora borealis. So um, these charged particles kind of flow around in the eddies of the magnetic field, and the magnetic field kind of ebbs and flows as well. And so sometimes those charged particles kind of dip lower into the atmosphere, and it causes a glow like a fluorescent lamp. So that's what the aurora borealis is. And then the aurora australis, I'm not quite sure if I'm saying that right, but I believe this happens in the southern hemisphere, and then aurora borealis is in the northern hemisphere. And it's really pretty, and there's a very wide range of colors that you can see, and they're somewhat unpredictable. There are stages of the sun's the sun goes through solar cycles, and at certain peak times we're more likely to see the auroras um, based on the cycle the sun is currently in. And so it's about an 8-year cycle. So you can't really be sure you can see them, but there's certain years that you have better chance of seeing it. And you also have to be above a certain latitude. If you Google this, you can see, it'll actually show you the band of where you can actually view the borealis, the aurora borealis. All right, compasses and magnetic declination. Now, a minute ago, I was talking about how their magnetic pole and the North Pole are not at the same place, and how that is weird when you're using a compass. And so looking at this image, this is showing, like, I'm not sure what year this is from, but here's the geographic North Pole, which is always in the same place. And then here is the magnetic North Pole. Now, crazy thing, the magnetic North Pole, or the or the South magnetic pole, as it would actually be, moves. So the magnetic pole is created by the flow of electrically charged ions in the core, and so the location of it actually moves around. And it moves around like on the scale of decades, not on weeks or something. So you would just need to know currently what the angle of declination is for your location, and you could accurately use a compass. But if you were, 50 years ago, it would be somewhere else. So you have to kind of, it does change, but just not very quickly. And so this is how I'm going to explain magnetic declination. So let's say that we are right here. Okay, let's say we're right here where this pink circle is, and we use our compass. Okay, we're going to use our compass, and we're going to point our compass and see where it lands. Now, our compass is going to point to the magnetic pole. And so it's going to point straight to the magnetic pole. Now, I need to know where the geographic pole is, because that's what's on my map. And so if I continue this line, you can see it's actually pretty close to crossing over the same point where the geographic North Pole is. So from my perspective right here, my compass is pointing to the geographic North Pole. Well, just about. I didn't quite get it perfectly lined up, but just about. So my compass is actually pointing to the South Magnetic Pole, or the magnetic North Pole, but because it's lined up with the geographic pole, it actually, well, I don't know how I just did that on accident. I just made that nice straight line. I do not know how. It essentially will get me to the right place. But imagine if I am here, okay? So then if I use my compass will point here, right? But I need to know here, because my map is based on the geographic North Pole, not the magnetic North Pole, because that moves around. So I have a problem. So my angle is off, right? I have this angle of difference between where I want my compass to point, which is the geographic North Pole, and where it's actually pointing, the south magnetic pole or the magnetic north pole, however you want to phrase that. And there's an angle of difference there. This is the angle, this is the magnetic declination. So we talked about, it's labeled a little bit higher up, magnetic declination. Magnetic declination is the change in angle based on your location of where a compass will point relative to the North Pole. So if I'm in this position right here, I have an angle that's off, right? That's probably about the worst it can be, is if you're like kind of dead center over here. That's the largest angle. But if you were to move, let's say here, okay, so then let me draw that angle. So then my compass is going to point there, but I want it to point there, and that angle is a little bit smaller. So depending on your perspective, right? Depending on your perspective, the angle changes. So the angle of magnetic declination varies based on your location, and you kind of need to know what it is where you are to be able to use your compass correctly. You can't just be dropped somewhere on the planet having no idea where you are and be able to use a compass to navigate, because if you are somewhere where it lines up, then your compass is pointing due north. If you are somewhere where you are in between the two, from the side and either side, you have to know that angle. Otherwise, if you start traveling where you think you're going north, you're actually going several degrees to the right of where you actually want to go. If you're on this side. Now, if you're on this side, it's the opposite, right? Because your compass is going to point there, but you need to go there. So you're going to be going too far to the left instead of too far to the right from the other side. Okay. So how does a compass work? It is north seeking. So it's going to point towards the north pole of the magnet or to the north magnetic north pole, or the technically south magnetic pole. Number 8, which end of a compass needle would point towards the north pole of a magnet? So the north end of the compass would point to the south end of the magnet. So the compass needle would point away from the north pole. So if we were to take a magnet and a compass, the red end of the compass needle would point away from that north pole of the magnet. And if we move the compass to the other side, it would point towards the south end. And this is how we come up with the whole magnetic south pole thing. Because a compass, when you take a magnet, it points away from the north end and towards the south end. So when it points towards the North Pole, that indicates that it's actually the South Pole in terms of magnetism. All right. Why does the amount of magnetic declination vary with location and time in terms of decades? So remember, location, I just showed you, depending on where you are, it lines up or it's off, right? And the amount varies with your location because of that. The other thing that varies, of course, is over time. So I don't have a picture on here of the location of the magnetic poles over time, but they move around. So it does matter when in time you are when you're talking about the location and the amount of a magnetic declination of a location. All right, last topic we have here is biomagnetism. Biomagnetism is a type of magnetism that certain animals have, hence the bio. Certain bacteria, they have this, they have a mineral called magnesite, which is essentially iron ore, and it forms internal compasses. And because iron is magnetic, it will attract them towards those magnetic field lines, either away or from, and they can navigate like that. It's pretty crazy. Pigeons also do that. They have magnets essentially in their skulls connected to nerves that allow them to know where they are. Crazy, crazy. So they can discern longitude and latitude of the earth due to the way the field changes based on where they are. Pretty amazing. Other animals that can do this are bees, butterflies, sea turtles, and fish. Okay, so this is more of into a review. So I'm going to stop the video here, and then actually I think I'm going to post a separate video of just the review. So I'm going to stop.